guys, so for this video I did an interview with my friend Kirby Runyon, who is a PhD in planetary geology. We talk about Mars, the moon, and the definition of a planet. So I hope you guys enjoy. Thanks! So Kirby here is a planetary geologist. So we're most likely going to talk about how the moon's a planet and Pluto's a planet in this video.
We can talk about other stuff.
No, I think we should talk about that. We should start talking about that because this is going to be fun. Okay, so tell me, what have you been up to? And you're doing a lot of exciting stuff right now.
Yeah, I've got a lot of projects going on right now. I'm working a lot on the moon, Mars, and Titan right now in particular.
So dope. Okay.
And in fact, where I work, the Applied Physics Lab, everything I have to say is my own words. Does not necessarily reflect the opinions of my employer. Okay, got that.
Okay. Yeah.
We got some study money from NASA to look at the Titan quadcopter. It's a mission called Dragonfly. It would send a nuclear-powered quadcopter to Titan later next decade, and it would land, take a bunch of measurements, fly around to another site, land, fly around, take a bunch of other measurements. The only other pictures we have from the surface of Titan are from the European Space Agency's Huygens probe. It's like one crappy picture from the surface, and that's it. And so we have the potential to see, like, what does this alien world look like up close?
Yeah.
If NASA selects this mission, Dragonfly.
And what was the reasoning for doing research on Titan? Because there's a lot of potential for there actually being life on there, whether traces of water.
Oh my gosh! So Titan is incredible because there's liquid methane seas on the surface. Underneath Titan's icy crust, there's probably an ocean of liquid water, and so what you actually have are potentials for two forms of life. In Titan's liquid water ocean, you could have traditional carbon-based life, a DNA, and it'd be kind of relatively warm temperatures above freezing. But on the surface, where methane would take the place of water as the solvent for life, you could potentially have silicon-based life that uses methane as its solvent at extremely low temperatures, around 90 Kelvin, which is like cryogenic temperature.
That's like freezing, yeah.
It's like liquid oxygen temperature, powers like the Falcon Heavy and stuff like that. So, but biochemistry would happen really slowly at these cold temperatures. That's not actually what I study, though, but I think it's cool.
Yeah. Wait, but you're studying more so...
I study the migration of sand dunes.
The migration of sand dunes. Wait, were you just in Buenos Aires? Are you allowed to talk about that?
Yeah, I can talk about that.
Okay, tell us. He was just in Buenos Aires because it's like the one part on planet Earth that can kind of be like similar to mirror the surface of
Mars.
Mars, right?
Yeah, well, so there's like two places on Earth. There's northwestern Argentina. Okay. It's actually near the city of Salta. Okay. And there and Iran. For certain geopolitical reasons, Argentina's a little bit easier. And so this area is covered with it's a volcanic deposit called an ignimbrite. It's nature's
Ignimbrite.
It's basically pumice.
Okay.
It's like nature's version of styrofoam.
Okay.
Some of these rocks are literally so porous they float in water. And that's what you use for like exfoliation.
Wait, this is like what they used on Zoolander when they're in the mine. Have you ever seen Zoolander?
I love that.
The moment he's like lifting all these rocks and then yeah, that literally was just like styrofoam rocks that used on set. So any of those actors out there, you guys know who I'm talking about. So okay, but this is like real. This is
real.
Amazing.
This is an ignimbrite flow. A volcano deposited these things, and then the wind there just whips through there every February. So it's like southern summer. So like right now.
Right now, yeah.
Gravel grains will be blowing in the wind up to 2 meters, like 6 feet high. It cracks windshields, like you don't want to be there during that time. Like the wind is whipping.
Oh my god.
So you can imagine that all this gravel blowing in the wind really just carves the heck out of this pumice in the ground.
Oh my god.
And so you have these beautiful, like streamlined shaped outcrops of rock. They look like battleships rising out of a sea of rock.
Oh my gosh. I'm
and I'll show you pictures. And just the rock formations are just gorgeous. This happens, like I said, in Argentina and Iran, and all over Mars.
Oh my god.
There's a geologic formation on Mars called the Medusae Fossae Formation.
Yes.
It probably also is an ignimbrite. It's like volcanic ash that's been sintered together.
Is it supposed to kind of look like Medusa because the snake's on her head and that's why it's named Medusa?
That's a great question. I don't know.
I think it is. We're going to have to research that. Okay.
And the Medusae Fossae Formation has all these other wind-carved features. They're called yardangs. Fun Turkish word. Yardangs, rock.
Yardangs.
Yes, Y-A-R-D-A-N-G.
Okay.
Rocks shaped by sand and gravel blowing in the wind.
Wow.
And so we're there to study landscape evolution, how the landscape changes. And so I'm a planetary geomorphologist. I look at rock formations on other planets. It's because I love the aesthetics of nature. And I love pictures from the surfaces of other planets and moons and asteroids. And you see these beautiful alien landscapes. And so geomorphology is the science of beautiful landscapes. So that's Argentina studying Mars. But Titan also has sand dunes all across the equator. And the weird thing is that atmospheric modelers who do numeric simulations of how Titan's atmosphere blows predict that the wind blows east to west, yet all of the sand dunes are oriented west to east. And so there's a conundrum there. Okay, how do you get that? And actually my PhD co-advisor has a paper written on that that says like, okay, so the wind usually blows east to west, but once like every century, you get the storm that blows west to east. And the rest of the time, the wind is too weak to pick up the sand. And so what some colleagues and I have started to do is to use a wind tunnel at the NASA Ames Research Center in Moffett Field, California.
Oh my gosh.
And it's the Titan wind tunnel.
Okay.
And this was built to be the Venus wind tunnel in the 1980s, because Venus also has sand dunes.
Yeah.
And it's been repurposed as the Titan wind tunnel. Now, Titan's atmospheric pressure is 1.5 times Earth's atmospheric pressure, but the gravity is only 1/7. That's less than our moon's.
Wow.
And so it's really easy to blow stuff in the wind because the air's so thick and the gravity's so low. Literally, if you had bits of like cloth strapped on your arms, you could flap your arms and fly. Like literally straight up on Titan.
I want to do this. Okay, so instead of a quadricopter, they should just make like a quadra spaceship.
They should send
fly
me.
us out.
They should send me with a squirrel suit.
Send us a squirrel suit.
You
It would be like a flying squirrel.
Yes. On Titan. We have these high pressure, we have the Titan wind tunnel. It's tubes that we put like sand simulant in, what we think the sand on Titan is kind of like. We actually use crushed walnut shells as like sand.
This is totally squirrel. Okay.
Totally squirrel. Yeah, because it's walnut shells.
Yes.
Because walnut shells are light. And so walnut shells are the same weight in Earth gravity what Titan sand would be in Titan gravity.
Okay.
So we do that because we can't dial back gravity on Earth, unfortunately. So, and so I'm actually in the middle of analyzing these data. I'm going to be presenting these results at the Lunar and Planetary Science Conference next month, March 2018.
Next month, March 2018. Okay.
So I have a 2-page abstract out on that for the conference, and I'll be presenting some initial results on that. But what's cool, here's another mystery.
Yeah.
I'm just going deeper.
Yeah.
So Titan's atmosphere is only between 500 million and 1 billion years old.
Okay.
Now, Titan is the same age as Earth, about 4.5 billion years old, and yet the atmosphere is only at most 1 billion years old. So what the heck?
Wait, that's so weird. So
young.
for a very long time, it didn't have an atmosphere.
Probably, yeah.
For a very, very long time, it was just still forming, I guess?
Just a vacuum.
It's just a vacuum.
Like every other moon in the solar system.
Yeah. Wow.
And so we don't know where the atmosphere came from. Maybe it started off thin and it's been thickening. Maybe it started off like instantaneously, like maybe all these comets hit or something, there's all this outgassing, it was really thick, and then it's been thinning over time. We don't know. So we've also done experiments at higher and lower pressures in the Titan wind tunnel to see how you blow sand on Titan at what we would call paleo pressures, at past atmospheric pressures. A colleague of mine, actually she's currently a PhD student at Johns Hopkins University. Her name is Xin-Ting Yu.
Okay.
She's also going to be presenting at the Lunar Planetary Science Conference next month because she actually makes Titan sand called tholins, which is a term Carl Sagan termed.
Okay.
Tholin. And it's basically hydrocarbon gunk. You take methane in the atmosphere of Titan, you electrolyze it with electricity, or you zap it with ultraviolet light, and it forms these really long hydrocarbon molecules. It's like cold gasoline, basically. If you took oxygen with you to Titan, don't, because it would blow up. It would blow up the moon.
Oh my gosh, that would be so bad. Wait, the moon or a planet?
It's both.
I mean, according to your, so let's get into your definition. The Planetary Geologist definition of a planet.
Yes. So, myself and a number of other colleagues consider a planet to be, it's a body in space that has enough gravity to be round, or basically in hydrostatic equilibrium with itself, to overcome the strength of its own materials, basically pull itself into a sphere, or maybe more accurately a triaxial ellipsoid. In any case, to be in hydrostatic equilibrium, where gravity has shaped it, where gravity is the main thing shaping it, but yet is low enough mass to not be a star, so not undergoing nuclear fusion or anything like that, or never have undergone that. So like a white dwarf star used to undergo nuclear fusion, not doing fusion now, but still not a planet. It's a stellar remnant.
Yep.
Okay, so we can, and that this is based on what it is, and it has absolutely nothing to do with what it's orbiting. It's what it is intrinsically. It's like who you are intrinsically as a person, not who your friends are.
Yeah.
But you define yourself on you, not who your friends are. Planets should define themselves based on what they are, not what they're orbiting. So with this definition, round things, or objects in hydrostatic equilibrium, orbiting other round things that we call planets would themselves be planets. And there's precedent for this. We have small stars orbiting big stars. Proxima Centauri is a red dwarf star, and it's orbiting Alpha Centauri A and B, which are G spectral type stars similar to the Sun. Those are orbiting each other. And Proxima Centauri is way out. You're orbiting both of these as a satellite star. Yet it's a satellite, yet it does not cease to be a star. Similarly, we have asteroids orbiting other asteroids, and yet these are satellites. So there's the asteroid Gaspra that the Galileo spacecraft flew past in the 1990s, and it has a small asteroidal moon called Dactyl. I love that name because it sounds like pterodactyl, which has wings and flies.
Flies like a flying squirrel.
And so Dactyl is itself an asteroid, and yet it's orbiting another asteroid. It's a satellite asteroid. It's a moon. So if you've got this precedent, oh, and galaxies. Like
Galaxies.
We're in the Milky Way galaxy. It looks kind of like the Whirlpool galaxy.
It's similar to the Whirlpool.
It's similar.
A little bit different.
But we've got satellite galaxies, the Large Magellanic Cloud and the Small Magellanic Cloud. They're small, dwarf, irregular galaxies, yet they're still galaxies.
They're still defined as a galaxy.
Even though they're orbiting us.
Doesn't matter about like the adverb for it.
Or the adjective, yeah.
The adjective.
They're satellite galaxies.
And
so the moon, our moon, for instance, it's round, it's in hydrostatic equilibrium, it has enough gravity to be that way. Geologically it's got a core mantle crust. There are volcanoes, none of them we think are active on the moon. There's moonquakes, there's faults, there's everything geologically happening on the moon, it's round. So by the way we think about planets, yeah, the moon's a planet. It's just a small planet orbiting a big planet. It's a satellite planet. And in fact, if you look at the word satellite, like natural satellite, it used to just be an adjective, not a noun. It's a satellite planet. That's how people use it. That's how Galileo used it. And that's how astronomers since Galileo, basically up to around the 1950s, used it. Satellite planet.
So crazy.
And then we just dropped planet, just called it satellites because we're lazy English speakers.
But then also where we like created things to actually orbit Earth.
Right. Artificial satellites.
Like GPS, and so satellites,
And so now satellite basically means spacecraft that orbits a planet.
And like everyone, literally uses the word satellite as that. No one has ever really heard like satellite planet unless you're actually in astronomy.
Right.
You don't actually know.
And so to those of us who are geologists and we study these things, the moon's a planet. We treat it like a planet. And so Titan, getting back full circle now, it's the second largest moon in the solar system, just under, I think, Ganymede, moon of Jupiter. Its atmosphere, though, if you count its atmosphere, it's actually the biggest moon in the solar system because its atmosphere is very puffy.
Okay.
But Titan's round due to hydrostatic equilibrium, and it's just a small satellite planet orbiting a big planet, Saturn in this case. And so it is both a moon and a planet.
Okay. But I guess, so now because you just said that, that's just why probably a lot of astrophysicists call it just the moon as opposed to a planet, because you have two different terms that can be applied to its definition. Where you said that it can be both a moon and a planet.
It's just like the Large Magellanic Cloud is both a
galaxy.
and a galaxy. It's a satellite of our galaxy, but it is itself also a galaxy. And what this does, see, when the words we use to name things help us think about them, conceptualize them, and it actually helps us to form scientific hypotheses, just the way our brains work. And if we understand planet to be a very broad term that encompasses really different objects, so like Enceladus, it's a tiny little 400 kilometer diameter moon of Saturn, and yet it's round due to it's in hydrostatic equilibrium. I would consider that, it's a planet. It's a tiny little planet orbiting a huge planet. And what this does is it shows you the huge spectrum of types of planets. Just like we've got a huge spectrum of galaxy types. We've got giant elliptical galaxies, we've got tiny dwarf irregular galaxies, we've got these medium spiral galaxies. Really different types of galaxies, but they're all galaxies.
But they're all still galaxies,
So Titan's a planet in this view. And by the way, if astrophysicists who want to use the orbit of something to determine what it is disagree with me and want to use their own definition, that's fine. I'm not saying everyone has to use my definition.
Of course,
Just like I don't want them telling me what definitions to use for my objects.
For the search for extraterrestrial intelligence and search for alien life, I think a lot of people tend to associate that with, oh, well, if we find an alien, it has to be living on a planet, not a moon. And so I think that's why a lot of people have these like contradictory thoughts about like Enceladus or Titan too, because they're like a moon. Like an alien can live on a moon or whatever, alien species. And it's like, well, I mean, that's the thing is I think a lot of people tend to associate the term moon with just like a dead, rocky object that's just kind of floating around in space, orbiting a planet where there could actually be habitable life. And so I think that bringing this term of planet and moon, I think is like really, really good because it's just going to make people have more of a broad understanding and like open-mindedness to there actually being life on not just other planets but on what moons are, because they're also, some of them can be considered planets.
Yeah.
Like geologically. What did you want to talk about next? Was it Pluto or?
I actually want to talk about our moon.
Okay, yeah.
Because you mentioned that people on the moon, on the moon, yes.
Yes.
And actually, here's Buzz's backside. This might not be Buzz actually, because
this is a picture of
that might be Alan Bean on Apollo 12 actually, because what this astronaut is carrying called the ALSEP, A-L-S-E-P, the Apollo Lunar Surface Experiment Package, and it was these geophysical experiments like seismometers and heat flow probes and lots of other stuff, solar wind experiments to measure stuff going on the moon's surface. So people think the moon, dry, dusty, rocky, boring. It's anything but boring. You know why? Because only the moon records the geologic history of both the moon and Earth from around about 4 billion years ago up to the present.
Okay.
Earth's geologic history from 4 billion years ago has been erased due to plate tectonics, this pesky stuff called life that's everywhere, and oceans.
So annoying. Oceans, life.
And an atmosphere. It just like destroys all the geology. Whereas the moon lacks these things, and it has that geologic history is still recorded. And one of the biggest geologic things happening 4 billion years ago was the pummeling of the inner solar system by asteroids. Big asteroids hitting really fast, like 20 to 40, 50 kilometers per second. Forming huge craters. So the moon has been cratered all the heck. Earth, because we're bigger, and we have 6 times more gravity than the moon, was hit even more than the moon was 4 billion years ago, but we don't record that geologic history.
Wow.
Now what's interesting is that is the same time when the first life evolved. At some point before life existed, we had geochemistry happening in the oceans, and then somehow through processes that we have not yet figured out, that geochemistry turned into biochemistry, and we have life. We don't know how that happened. But it happened in this environment of getting pummeled by giant asteroids that would vaporize the oceans and melt the crust of the planet into lava. And so life can't exist in that. And so life had to evolve once that was done. And so by understanding the impact cratering history of the moon, we can infer the impact history of the Earth 4 billion years ago and understand the environment that the very first life would have evolved in. And that fascinates me because this is origins of life and its astrobiology. How does life start on our planet, and how does life therefore start on other planets or moons?
Yeah.
You know? And so by understanding how life starts here, by studying the impact history on the moon, we can understand how life may start elsewhere in the solar system or universe.
Yeah, I mean, well, couldn't the impact of an asteroid have actually brought over something to the planet that could have spun off of life,
Yes. I mean, the planets were exchanging materials.
Yes, it's just like pollination. Cross-pollination too happening on Earth with bees and
So there's this process called spallation.
Spallation, is that like pollination?
In this context, kind of.
Kind of, but like on a planetary scale?
So when an asteroid hits like, say, Mars or something, the shock wave rebounds off the surface of Mars, and then there's a rarefaction wave. So compression wave is the shock wave, and then it expands, it rebounds. That's a rarefaction wave. And when it hits the free surface of Mars, that sets off a process called spallation, and rocks get shot off into space at a greater than escape velocity.
This is so cool! My gosh.
And they go into orbit around the sun, whereupon they can sometimes impact Earth.
Wow.
Now the same thing could happen with Earth.
So cool.
So there's probably meteorites on Mars that fell out of the sky on Mars, but actually came from our planet. Probably the same thing for Venus and Mercury.
Yeah.
And so the planets were exchanging materials, especially 4 billion years ago, when asteroids are it was much more common for asteroids to hit planetary surfaces then.
Wow. Well, I'm like totally blown away by like everything right now. So we can literally go on for like probably another hour talking about all this.
Yeah.
But thank you so much for talking.
Thanks for having me on.
Cheers.
Cheers.
That was like super dope. Maybe we'll do like a part 2 video talking about planetary geology. And just so everyone can find you, is there a Twitter handle, so Instagram that everyone can find you at?
So I'm mostly on Twitter.
Okay.
You can find me at NASAman58.
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 Why the number 58?
I'm so glad you asked. The year 1958, which is the year NASA came into existence, specifically October 1st, 1958, which is the start of the federal fiscal year.
Wow.
It was a result of President Eisenhower signing into law the National Aeronautics and Space Act of 1957 that then created NASA effective October 1st, 1958. So an homage to the beginning of my favorite government agency, I chose 58 to be the number at the end of my username, so NASA58. And NASA Man just because I love NASA.
Yeah. Amazing. Well, thank you. Now you guys know where to find him. So I will talk to you guys next time. Do leave a comment and please do subscribe. Leave a suggestion for any type of topics you guys want to hear next.